Okay, I start the example given in the paper. Design a PID controller for a 2PD1 process where K is given to 2, T1 of the process is given to 0.275 seconds, and T2 is given to 0.165 seconds. And I select the sampling time for you. The sampling time should be 55 milliseconds. Okay, this example should be demonstrated also with simulation and with all aspects. I think you will see after this final result will be a well done PID controller in digital way. Okay, so first note the sampling time is not smaller than 0.1 times the largest process time constant. So not true. Not true. So recommendation of my choice of sampling time 0.1 is violated. 1 is violated. I have done this because you should see also in spite of a very large sampling time, larger than normally recommended. Normally 1/10, the sampling time should be smaller than 27 milliseconds. I take rather the double value. So the idea is to show you, in spite of this rather large sampling time, we get a good design with these design steps. That is the goal of my example. So what I have to do is, okay, I draw the signal block diagram, which I have to use in my simulation program, which I will use for designing the controller. Then we add the process gain to 0.275. Then the second PT1 block is added. Here gain 1, 0.165. And now, don't forget the delay time block, which is necessary if we want to have a good PID design. And then there is a feedback line with a negative sign. So this is desired value, controlled value, controller output value. This is the signal block diagram of my example. TD, I want to use a real algorithm. Then, of course, we have no hardware. This should only be simulated, the system. Take a real algorithm for worst case delay. The delay time then is half of sampling time plus a complete sampling time for the calculation time. So we get 1.5 times 55 milliseconds. This should be 82.5 milliseconds. So this is a delay I want to add if I make the design in a good way. So first I make a design, note the parameters of my PID, and second step is I want to simulate this system in our digital simulation system. So what you will see now in the next step is the design done with our analog Regc simulator. Test with WinDF C#. That is a tool which can simulate digital systems. So I want to make 3 designs. I show 3 different designs. First, I want to show you a simple PI controller. Note that a PID and a PI takes the same steps, the same simulations. Now the PI controller has a step depth of 1. So all things for PID is valid also for a PI. The only parameter what you have to note is that the step depth is 1. So PI first, then second, I want to show you a PIDT1 with step depths. Let's just check the step depth estimation in our system is 1. Note in pole compensation, the largest process time constant should be copied into the Tn value, and the second largest process time constant should be copied into the TV value. So pole compensation here is used so that we directly can calculate the step depth estimation as 1 plus TV divided by T0, and the value you get, if you divide the TV value by 55 milliseconds, this is exactly factor 3, so we get a step depth value of 4. So we design first PIDT1 with step depth 4, but first neglect delay. So delay time TD is 0. I want to show you this because this is the result will be that if you don't use my design steps, if you ignore the delay time of the digital controller, you will see what happens. I will promise you the loop will be unstable. And the third design is then the correct design, step depth 4, and delay time is 82.5 milliseconds. So I now go into the Regc program, show you the results, and we note the queues. Result from Regc. 1, we get a Q0 and a Q1. 2, we get 3 Qs and Q2, and finally we get a third design with also 3 Qs, so that this is the resulting table, I will say, for all 3 designs. I start Regc, try to find out these values, show you how to get these values. Then I have to copy these values into my design program WinDF C#, and then run all 3 loops, and you will see the results then after some minutes. Okay, I have started Regc in version 3.19. I want to do the job now with mouse, not with pen. It's a little bit more easy for me, and you can see the mouse working. Yeah. First, I add the controller. The controller is behind this block. Oh, you see, if you start, menu language is German. So I want, of course, to show you the English menu, or we want to work with the English version. No problem with this. The controller, the designable PIDT1 controller, is behind the block Reg, from German Regler. Yeah, this block we put just anywhere on my drawing area. we ignore these values because the design program throws out the correct values. So I say OK and add now the both PIDT1 blocks for my given example. Note the gain is 2 and the time constant is 0.275. Second block added with gain 1 and the time constant is 0.165. And yeah, that's all. Now we need a summing point. Put it there. We need branches. I go into the branch mode. You see 3 new buttons since version 3.19, which I think is a little bit more helpful. If I click on this, you see this has a blue mark. Here you can see we are now in the branch mode, and if you want to leave the branch mode, just click on the pointer button or any other button of S or M. In the branch mode, you can now add branches with 2 mouse clicks. Starting, ending point is each one click. Click, click. You see the working is very simple. Close the loop. Note that I ignore at this point the delay time block. Yeah, the PI also has no delay. Yeah, the next step is I need a minus sign. Go to minus sign point. You see then automatically the branch mode is disabled. And if this button, the minus button, is marked, then I have to look for a branch, click with the mouse exactly on the branch, then this branch get an inverter. In the drawing you see there is a minus sign, and automatically the minus sign mode is disabled, so you can only set one summing point, one minus sign, but multiple branches. Okay, that's now my signal block diagram. I can directly go into the controller design method, click on controller design button, then accept this window, simple loop, so the values here are just good proposals. We have no depart, so leave this checkbox inactive, say OK, and now the controller, PI controller should be defined. The controller makes a proposal. This is default value of the program, doesn't fit to our program. We want to have pole compensation, so manually we type in our largest process time constant we know from our example. If you have no idea of time constants, you of course can take this proposal. You see not far away, set of 275, 330, that is a good proposal. If you want to have a proposal, just click on this button. I don't want to have this because I have a manual setting of pole compensation, so very simple. This is true. All designs should be done. I have not told it in the paper. I want to do this with a 60-degree phase margin. So if I leave this with PI controller, I get the Bode plot curve with fine lines. Just this is an information we really don't need, because if I close this window with the close button, then the design result is displayed and automatically stored in a report file. But I think for our purpose, we note now the gain is interesting, 0.555, and the time constant is set manually. I know this. So the only thing what I have to note is the gain 0.555. So let's go back to the notes, and I can make a remark. I can say KC is 0.5555. Now we have to calculate the Q0 and Q1. This of course can be done with a program, or you can just simply use our equations. I show you the way with the program. Yeah, I go back to the program. I close this window. I don't need it. I have noted the results, and what you should know is there is a PID converter. I open with a right mouse click the parameter box of this controller. Here you see the resulting of the design. Step depth is 1. And look for this button. This is a PID T1 controller. If I open this window, then you see several blocks in this diagram. All blocks represent a PID controller. This is a Bode form, parallel form, wiki form, analog hardware, digital hardware, a digital parameter box. So I replace the sampling time in this window to 55 milliseconds and click on design method 1 we discussed now, and the program calculates the Q0 and the Q1 value. Note, simple to keep in mind, Q0 is 4.6 and Q1 is negative 4.5. That is accurate enough in our purpose. So I note 0.6666 and negative 0.5555. The K value. You see negative K value in the Q1, and here the time constant, the sampling time is used. Okay, so far we have designed our first controller, and go back into the design and close the converter window and close the PID window and go back to controller design, and we want now to design the PID controller with the differential part, the PD T1 part, and here you see also you can either accept the proposal, but in our example we know the second largest time constant is 0.165, so we manually type this in, ignore this proposal, and replace now my step depths to the value of 4. Say OK. Here we can accept this, the values from the previous PI, unchanged PI design. Click on PID T1 button, and then you get the Bode plot of the system. Of course, here you can find where is a crossover frequency. Here's a 0 dB. Crossover frequency is a little bit larger than 10. You want to have fine lines, 0. So I guess the controller crossover frequency is say 14. And the rest is done automatically. So I close this window and get the result. You see K has 2.222 and TN and TV is set manually, and step depth also set manually. Yeah, here omega D is 14. So I note this result in my OneNote examples. Q0 is 2.222. Sorry, I'm not ready with this. Oh yeah, the Qs. We have to calculate the Qs. Here I can calculate the KC. KC is 2.222. TN is 0.275, TV is 0.165, step depth is 5. Here TN, that is KC, yeah. TN is 0.275. So now we need the Qs, the 3 Qs. So I have to go back into the Regc program, open with the right mouse button the PID window, open the PID converter, and just click on this button. Then the program calculates the 3 Qs of my second design. So 10.666. 10.666. Q0 is negative 16888. And Q2 is 6.666. Okay. 6.666. Okay, so that is our second design. Now I start with the third design. I have to go back to my Regc program and now add the delay time block. So I show you how easy it is to change the block diagram. So I'm in the pointer mode. If not, click on this, then you are in the pointer mode. Then you can point on some devices. For example, I point on this branch, then go to my keyboard and click the delete button, and then all marked elements then are deleted. I add now a delay time block, that is this part. I put it here and change the delay time to 82.5 milliseconds. Yeah, no time is in second. Say OK and go to branch mode, close the loop, and then we can repeat the controller design now with the added delay time block. Yeah, controller design, starting, accepting these numbers unchanged, don't change this and that are the values we want to keep constant. Say OK, keep these contents, just click on PIDT1. Don't be confused with this red curve, that is a phase caused by the delay time block, which is here. Of course, in this diagram, the phase is wrapped, we say, so that the phase scale is unchanged for a full period, yeah, from negative 180 to plus 180. We leave this and note the new KC. The only value which is important for us is the new KC value 0.5925. Close the loop. 0.5925. I just write it here. KC is 0.5925. Rest unchanged. Yeah, like version 2. Okay, we need the 3 Qs. So I have to go to the PID converter. Each time automatically the number 4 is selected, so please go back always to the design 1, and here the 3 Qs are calculated. 2.844, negative 4.503, and finally the Q2 is 1.77. I round up to 8. Yeah, 1.778. 1.778. Try to redo this design with your own program, and try to do the right settings, and then you should get the same results. Yeah. In additional exercise task, you get a new process with new values, and then you should redo this and send me just the final results. Note that in this program there is a reporting page behind this button, open close the report panel. If we open this report panel, then you can see here the 3 design results as a text file. And you can store this text file if you want, yeah, and have a good reporting page. If you want to have the resulting controller values also in your report. Oh, I'm in the branch mode, you see. Okay, I want to be in the pointer mode, in the branch mode. If I click on this button, go to PID converter, then if you want to have a report of all values, go to this button. I click this button with the last design, stop, with the last design to report, and if I close this and open the report button, then you see, if I look here, the results of the digital controller here with sampling time and with the 3 queues. Yeah, that could also be a good way, yeah, to use the report page here in this program. Okay, so far I have done the simulation of the analog system, the design of the controller, calculation of the Q values. Now I can start with the digital simulation of the real digital controller. This comes up with a new video.